Dear students, in the last class we have discussed fixed bias and equations. Now we will see on problems relevant to that. So in this problem you can see this is a fixed bias circuit because the RB resistor is connected in series between the base terminal and the supply voltage. And your supply voltage is 12 and your the given collector current and VCE voltage. Okay, so here what we are going to find is for different values of beta like a 50, 100 and 150, we are going to see how the operating point is going to change. What is the stability of this circuit? That is the concept of this problem. First, we will be finding what is the RC because the RC and RB is not given in the problem because they are given collector current and the supply your output voltage VCQ and the supply voltage 12 and beta they given us 100 for this. The beta they given us 100. We want to find what is the RC, RB, IBQ to find. So I will find very simple. First, we will be applying the KVL across the output flow. When you apply the KVL across the output loop, what will you get? Plus VCC minus entering at a plus, leaving at a minus. So minus ICRC. This entering at a plus, leaving at a minus. So minus VCE equal to 0. From this, I can get RC to VCC minus VCE divided by IC. I can write it as VCQ and IC because this is DC analysis, this both are same. So this is the formula they have written. So what is a VCC 12? What is a VCQ 6? And what is a ICQ 1? So 12 minus 6 divided by 1. So we will be getting here ICQ is milliamps, right? So when it comes, it becomes kilo. So 12 minus 6 will be getting 6. So 6 divided by 1 into 10 to the power minus 3, we will be getting 6 kilo ohms. So this is the way how they determine RC value. Now we know the relation IC equal to beta times of IB. How you got that is a beta is a gain factor, output current by input current. So IC by IB. Here I want IB, right? So IB equal to IC by beta. That's it. We will be getting, that is what you determined is 1 milliamp. That is given in the problem. 1 milliamp divided by 100. So we will be getting 10 micro amps. That is micro is nothing but 10 to the power minus 6. That's it. Now I want to find what is the RB. So I will find, you want to apply the KVL in the input side. Apply KVL. What you will get? Plus VCC entering at the plus, leaving at the minus. So IB RB entering at the plus, leaving at the minus. So minus VBE equal to 0. What we want to find is RB. So RB equal to VCC minus VBE divided by IB. What is the VCC? 12. What is the base emitter voltage for silicon? 0.7. Divided by what is the IB? Determine 10 microamps. 10 into minus 6. What is the answer? 1.13 mega ohms. If you substitute in calculator, you will get 1.13 mega ohms. So we got RB, RC, and IB. We got all the required values. Now we want to draw the DC load line. Then we want to fix the operating point. That's it. Okay. Now we'll see the load line. What is the master equation? Already explained you. VCE equal to VCC minus ICRC. What is the supply voltage? 12. What is the IC? What is the IC? 1 milliamps. 1 milliamps, right? 1 into 10 to the power minus 3. What is the RC? RC, the given we determine value is 6 kilo ohms. So 6 kilo ohms plus 3. So both will cancel. So 12 minus 9. It is a VC. Okay. 12 minus 6 voltage. Right? So this is a master equation. Right? So these values you keep aside. So now you draw the output current and output voltage. Now what is the procedure? Case 1. What is the case 1? We want to find what is the maximum VC. So in that condition we want to consider IC 0. You consider IC 0, this equation becomes what? BCE equal to VCC. What is the VCE here? VCC is given as 12, right? So 12. That's all you got X point. That is 12. Now case 2. What you want to find? You want to find maximum IC current. That means VC is 0. So consider VC is 0. So IC equal to VCC by RC from this formula. You consider VC is 0. So that is from here I have written VC minus IC RC is nothing but IC equal to VC by RC. So what is the VCC? 12. What is the RC? RC is 6 plus here kilo ohm, right? So if you cancel, what you get? 2 milliamps. That's all. So you get 2 milliamps. So that's it. Now you connect this. So this is called DC load line. So now we want to find the operating point. So first we'll go, now we got a load line, right? So now we'll go to the operating point. Very simple procedure. See here. So I'm duplicating here same IC VC. So here we got 12, here we got 2 milliamps, right? So I connected this. Now I want to find operating point. First I will be taking for 50. Then we'll be taking 100. Then we'll go for 150. When you take a 50, the same the collector current is 0.50 and supply voltage is, your output voltage is 9. Similarly, you can see the ICQ varying when you go for 100. So that means you can see for the changes of transistor parameters, the operating point is keep on varying. So that says this circuit provides the poor stability. How these values are obtained, we will see. First, we will take 50. Okay, so first we will calculate the VCQ value. So VCQ, what is the supply voltage? 12 minus what is the IC? So IC is nothing but a beta times of, so we will take for 50. So what will get? 50 into what is the IBQ? 10. So what will get? We will be getting 0.50 milliamps because this is microfarad. So if you multiply 50 into 10 to the power minus 6, you will get 0.50. Right? So that means 0.5 milliamps into what is RC? That is 6. So what is the answer? You will get 9 voltage. So what is the ICQ? What ICQ is nothing but a 0.5 and your VCQ is 9. This is for when beta is 50. Similarly, we will put for 100. So this is a load line and we will find what is ICQ and VCQ. We will consider beta as 100. So what is ICQ? 100 into 10 into 10 to the power minus 6. What you will get? You will get 1 milliamps. So here we will be having 1 milliamps. Just assumption 1 milliamps. So this is because this is 2 milliamps. We take a 1 off. This is a 12 voltage, right? So another one VCQ we want to find. So 12 minus what is the IC? Is 1 milliamps. 1 into 10 to the power minus 3 into 6. So what it's a kilo ohms, right? So both will be cancelled. So we'll be getting 6 voltage. In the previous case, in the 50 it was 9, now it is 6. So 6. So this is for when beta is 100. When beta is 50, what you got? You got 0.5 and you get a voltage of 9. This is for when beta is 100. Similarly, when you go for 150, you are getting 1.5 and voltage is 3. So you can see the variation, how this Q point is varying to the higher level and lower level, the changes of beta. So this is for beta is 50, this is for 100 and this value for 150. When beta is varying from 50 to 100 and 100 to 150, you can see how these points are varying. So in 50 you can see 9 volt, in 100 you can see it was 6, in 150 it was 3. That means the values are changing with respect to transistor parameters. So stability of the circuit is very poor. So that is your understanding from this problem. Similarly, I have given another problem. I have given the class, right? So that problem you can try. If you have any doubt, we will discuss in the class.